To the last video on AC circuits. In this video, we'll talk about power in AC circuits. So there's one main equation that we'll have at the end of this video. So the book has, again, it has you look circuit element by circuit element. So you have an AC source, and then you can have three different things here. A resistor, a capacitor, and an inductor. And then we'll think about what happens if we put all three of them together at the end. Most of the interesting stuff happens if there's a resistor here. So we'll talk about that in a second. So we'll start with the resistor. The power dissipated by a resistor as a function of time. Well, the power dissipated by the resistor at any moment in time, maybe let me not scare you with the T. P is equal to I squared R. Now, in this chapter, we got to be a little bit careful, lowercase versus capital letter. So I'm going to immediately replace this with, it's the current at that time. And this will be the power dissipated by the resistor at that time. And the issue is that in AC circuits now, the I as a function of time is sinusoidal. So like if I of t is a sine or a cosine, maybe with some phase angle, I squared is going to be a cosine squared or a sine squared. And so you can see this in this graph right here. So the maximum power dissipated by the resistor at an instant in time is this I squared R. But it also goes down to zero sometimes when there's no current going through the resistor. So it keeps going back and forth between dissipating power and not dissipating power. So these AC sources are often very fast. So for example, in your home, the 60 hertz. And we don't really care about what's happening at a single moment. We care about what the average power dissipated by the resistor is. Because really after 60 cycles, you wait 1 second or even a fraction of a second, you've undergone a lot of cycles already. So you can basically just take the average because, yeah, I don't need a reason. Yeah, so the average value of the power dissipated by the resistor is the average value of a cosine squared function. So maybe your math professors talked about this a lot or not, but cosine squared of x, the average value, and here we're actually averaging over time. So maybe cosine of omega t. The average value, you might use like square brackets for this. You might use a line for the average value. Or if f of t is this, then the average value is like the line over it like that. The best way is probably just to write the word average, just so everyone knows what you're talking about. The average value of f, if you average over a integer number of half cycles, is 1/2. So, cosine squared bounces between 0 and 1. It kind of makes sense as 1/2 because like cosine squared and sine squared look very similar, just with an offset. And you know that the sum of the two have to equal 1. So if the sum of the two is 1, then each of them averaging 1/2 kind of makes sense too. So anyway, this is the average power dissipated in the resistor, where I sub R is the maximum current, the peak current that's going through the resistor. This function is not the function we're used to. So we're used to seeing P equals I squared R. And we really like I squared R. We don't like this random factor of 1/2. And when it comes to power, it becomes nice to not talk about the peak values of these quantities, but actually something called the root mean square values of these quantities. So you can take any of the peak values that we talked about before. So the voltage across any device or the current that's going on in the circuit. You have, so whether it's a V or a I, so just call it A, it could be anything. You have the peak value, and then you have the RMS value, which is the peak value divided by square root of 2 is A RMS, root mean square. This is true as long as there's a sinusoidal function, and this is the amplitude, the peak value of that sinusoidal function. So root mean square means, you kind of have to read it right to left. So you square the function, you take the mean or the average, and then you take the square root again to get back to the original dimensions of your quantity. If you do that for a sinusoidal function, you get 1 over square root of 2 times the peak amplitude. So the root mean square current is the peak current divided by root 2. And notice how if you plug this into, or if you replace this formula, the peak value I sub R, the peak current going through the resistor, with the IRMS, you actually recover your original formulae for power dissipated by the resistor. You get I squared R, or you get V squared over R, as long as you're talking about the RMS voltage across the resistor, or the IRMS through the resistor and the VRMS of the resistor. And also for the source, so the source is supplying the same amount of power. So remember, our circuit is just this and the resistor. So they have the same VRMS. VRMS of the source and VRMS for the resistor are the same. So instead of the resistor, you could talk about the source. The source is RMS. And this is actually the 120 volts. So in your wall outlets, when they say 120 volts, that's the VRMS. That's the thing that we can more easily measure. Well, whether or not it's easier to measure, it's what's more relevant when we talk about energy. A lot of times when we're dealing with power and electrical outlets, we want to know how much energy we're using, power we're using. And we recover some formulas that we know. So by that I mean like P equals IV. So that's true as long as you're using RMS values, not the peak values. So the power supplied by the source, so the EMF source is supplying energy to the circuit, and the resistor is dissipating that energy away as thermal energy, and they're equal just from conservation of energy. For capacitors and inductors, they don't dissipate energy, right? They're just temporarily storing energy. For a capacitor, you're temporarily storing energy via the charge separation or via the voltage. And then for an inductor, you're temporarily storing energy via the current. But the energy, you're giving energy to these devices and then you're taking it away again. So the source is giving energy to, say, an inductor. I'm imagining a circuit that looks like this. The source is giving energy to the inductor and then taking it back, and then giving it to the inductor and then taking it back. Overall, neither of these two circuit elements have any average energy dissipation or are supplying any energy overall to the circuit, or they're not being powered up. So you get these two other equations here, that the power for the capacitor is 0 and the power for the inductor is 0. So this is the power supplied by the source or dissipated by the object or supplied by the object, any of those things, because the energy is bouncing back and forth. The rest of this section is talking about, well, what if we put all of these things together? So what if we look at an RLC circuit? What equations do we need to know for that? So the answer is that we can use our formula before, but we have to modify it a little bit. So this cosine phi is going to wind up taking into account all of the different cases. So if we just had a resistor connected, if we just had an inductor, if we just had a capacitor, it would be taken into account right there. So let's see why this is. So we can prove this pretty quickly, separately from the way that the book does it. So the power, all of the power either supplied by the EMF source or dissipated by the resistor is dissipated. I should probably phrase that differently. All the power that's supplied by the EMF source goes to it being dissipated by the resistor. Nothing overall interesting in terms of energy with the inductor or the capacitor in terms of where the energy goes. So the average power dissipated by the resistor is the 1/2. Actually, we like the RMS value, so let's just stay with the RMS values. It's IRMS squared over R times R. I'm going to rewrite this way. IRMS squared Z times R over Z. So all I did was I multiplied and I divided by the impedance of the circuit Z. This is going to be the impedance of this whole AC circuit. So you can prove, well, okay, so let's first focus on this piece. IRMS squared Z, I can rewrite this as IRMS times Z. And this is IRMS times E RMS. remember V equals IR, like, and for the source, it's E peak equals I peak times the impedance. But then if we took that equation, maybe it's difficult to follow when I'm saying aloud without it being written. So what we've seen before in previous sections was E naught was I times Z. And so these were peak values. We didn't write the subscript P, but we could have for the peak current. So if you take this equation and you divide both sides by square root of 2, you can also get the equation that E RMS supplied by the source is I RMS times Z. So this is like the V equals IR, like the Ohm's law, but for complex impedances, so for AC circuits. So you can have RMS value, or peak value, and it's still the same equation because you're dividing by square root of 2 on both sides of this. So P, the average power dissipated by the resistor or supplied by the source, is IRMS, ERMS times this thing right here, this R over Z. It's kind of keeping track of, well, okay, we've seen this before. This R over Z is, if you drew a phasor diagram, so you have this voltage, and say you just have an inductor, so it looks like this. So the source would be the sum of those two things. This would be E for the source. This is VL, this is VR. This angle phi, one way of writing it, one way of writing that angle phi is actually cosine of two things. So let's see why this is. Remember we had a triangle. So this, and this would be our triangle here. This would be R, X sub L, and Z for this phasor diagram. So this is, you could draw this triangle for the voltages for V sub R, V sub L, and then the source EMF, or you could draw it for just the resistances and the reactances and impedances. And this is the angle phi. So notice, since this is a right triangle right here, cosine phi is R over Z. So when I say we've seen this factor before, what I mean by that is we can relate it to the phase angle of our circuit. So phi is the amount by which the source is leading the current. Cosine, then that's the phase angle of our circuit. And then you have to take that factor into account for when you're multiplying the P equals IV. This factor is, and you can double check this. So if you just had a resistor connected, phi would be 0. So you would get the formula that we had before at the very beginning of this video. And if you plug in phi is plus or minus 90 degrees, so plus 90 degrees for just an inductor connected, or negative 90 degrees for just a capacitor connected, you'll get that the average power supplied by the source is 0. Yeah, so this nicely generalizes our results so that you can talk about any combination of those quantities. You just have to remember that power factor, cosine phi. Okay, so let's take a look at the example problem here. So it looks like we have the average power supplied by the source is 0.707 watts. And it looks like that's not equal to IRMS times ERMS. So the formula that I'm thinking of is that the average power supplied is IRMS V or ERMS times cosine phi. And if we plug in numbers, we get 1.00 amps, 1.00 volts, cosine phi. It looks like cosine phi is 0.707. And that's actually very close to 1 over square root of 2. So if you actually plug this in your calculator, you'll see phi is either plus or minus 45 degrees. Maybe even another significant figure here. Now, nothing in the problem statement told us whether this phase angle should be positive or negative. We don't know if the inductive reactance is bigger or the capacitive reactance is bigger. And remember, cosine phi looks like this. This is cosine phi as a function of phi. Phi is 0, cosine phi is 1, and drops down to 0, these two sides, but it's always positive. So this equation right here doesn't uniquely tell you what phi is. It tells you it's plus or minus 45 degrees, but we don't know which one of those two. So there's two possibilities for the circuit. So it looks like the power factor, so we didn't actually answer part A yet, but the power factor, cosine phi is 0.707. And for part B, so we're given a resistance and a inductive reactance value, and we want to know the two possible values of the capacitive reactance. So the fact that cosine phi is, so we can do this algebraically or visually using the phasor diagrams. So let's do it algebraically first, and then we'll see how this works out on the phasor diagram. We have an equation for phi. Phi was arctangent of xl minus xc over r. And we know that this angle is 45 degrees. So tangent phi, so if you know that phi is 45 degrees, this is phi, you know that, so if you know phi is plus or minus 45 degrees, you know tangent of 45 degrees is plus or minus 1. So taking the tangent of both sides of that equation, you get, so tangent phi, which is plus or minus 1.00 here. This is xl minus xc over r. So you can start to see why the problem statement is saying what are the two possible values of x sub c, because we have to split this off into two pieces. Once where that value is plus 1 and once where it's minus 1. So let's look at those two cases. So if it's plus 1, then you can set up an equation r is xl minus xc. And we're solving for x sub c. So x sub c would be x sub l minus r. And it looks like we have 200 minus 50. So 200 minus 50 ohms, or 150 ohms. So one of the possible values is 150 ohms for the reactance of the capacitor. The other possible value is if we take the negative one, so negative 1.00. So we can have this equation, minus r is xl minus xc. Xc is the sum of the two. Sorry, my L and C is looking identical. XL plus R. So this would be 250 ohms. So the two possibilities are that the capacitive reactance could be 150 ohms or 250 ohms, because the difference between that and the inductive reactance has to be 50. So notice how the X sub L is 200. And the difference between 200 and a number has to have absolute value 50 ohms. Whether it's positive or negative, we don't know. But it doesn't matter for the power factor. So power tells you some things about the circuit, but it doesn't tell you whether the source leads the current or vice versa. In terms of a phasor diagram, so if we drew, say the current phasor, this right here, and then the voltage phasor here, here, well, so I don't even want to draw the phasors. I just want to draw, this is the resistance. Because remember, you could draw voltage phasors, like the 3 voltage phasors, but then do a similar triangle where it's just resistances and like impedances. So we have a resistor that's pointing this way. We have a inductor that's pointing this way. And then we need to add so this is the X sub L, which is 200 ohms, and this one was 50 ohms. So we need to add an inductor value so that the sum of the 3 phasors is 45 degrees with respect to this vertical direction. So we could add all the way up to here, or we could add up to here. But we need to have, like, this XC value would need to be such that this is either 50 or this is 50. So there's those two possibilities. So it could be the 200 plus 50, or it could be 200 minus 50. And that's exactly what we saw algebraically. Uh, okay.